Okay, today we're going to start with week 5 homework answers. And first of all, I want to give you some formulas that I think are critical for this chapter. The first of these has to do with the two friction formulas. One is the friction for static friction, and the other is kinetic friction, and both are fairly straightforward. The first one is the coefficient of static friction times the normal force, and I'll explain what normal force is in just a second. The second is the coefficient of kinetic friction times the normal force. And so your static friction, which means the initiation of motion against friction when the object is solitary, is found with this formula. And then once it is moving, then it changes from static to kinetic friction. And all of you have experienced the fact that getting something started is more difficult than keeping it moving once it has started moving. Now, in order to do this, you have to know that the normal is the force that is perpendicular to the surface. So regardless of the slant of the surface, the normal is always perpendicular. And so if you're on a slant, weight many times is straight down toward the earth, but the normal is always perpendicular. Now for these problems, I believe that all of these remain flat surfaces and don't talk about, well, except for problem number 13. However, always remember that the normal is perpendicular to the surface, and it is the force that's used to calculate the friction force. So that's the first problem, or the first equation or set of equations that you need to make sure you understand and get on your card. The second is the equation for drag, and there's actually two of these. The first one is the overall equation for drag, which looks like this. And I'll explain the symbols here in just a second if you haven't already figured them out from looking at the chapter. So the drag force is equal to 1/2 times C rho A V squared, where C is the coefficient of drag and rho is the density of the medium which it's passing through. A is the surface area that's exposed to the medium that it's passing through, and then V is the velocity. And as it says in the book, for large objects, the drag is directly proportional to the square of the velocity. Now this changes when we start talking about smaller objects, but this will be the equation that you'll use for larger objects. And there's a table in the book, I think it's table 2 or 3, it might be table 2, where the coefficients of drag of certain materials are given, or certain cars, and so forth. And density, sometimes you have to look up density on Google or on the internet. And then many times the problem will give you the surface, but there's also in the table, there are tables to look at surfaces depending on what the situation is. Now, an alternative formula to drag for situations where you have an object that's very small is called Stokes' law. That's why this little s is here. And Stokes' law changes the coefficient of drag, changes the force of drag by the following. And the important part here is the velocity. It's related to not square of the velocity, but straight related to the velocity. So you have 6 pi times the radius. R represents the radius, 6 pi times the radius, and this symbol, which is the lowercase nu, represents the viscosity of the medium that you're passing through. And again, sometimes you have to look that up online. And then V here is the velocity. And the key difference is when objects are extremely small, like bacteria or dust or pollen, things of this nature, instead of being related to the square of the velocity, it's related to the single or the just the straightforward velocity. The last two equations I want to go over are related to the change in length when a force is applied to a material, and the change in perpendicular movement or stress, let's call this shear force, when a force is applied to the material. And these are the two equations that I want to look at. This one is called Young's modulus, and this is called the shear modulus. This tells you how much longer or shorter something becomes if a force is applied along the same axis as the length of the material. And this tells you how much perpendicular change in a material there is if a force is applied perpendicular to that object. And Y here is Young's modulus. F is the force applied to the material or an object, and A is the cross-sectional area, and L0 is the original length of the material. S stands for shear modulus, and the others are all the same. So one represents the change in lateral change, and the other represents the longitudinal change. So with that review, let's start doing some problems. And the first problem that was assigned was problem number 3, I believe. Yes, problem number 3. And in this problem, you have a mass of 66.0 kilograms. And this mass is pushed along, and the question has to do with how much friction force occurs. And in order to do that, you have to look up in table 5.1 the friction, the static friction coefficient. And the static friction coefficient is 0.016 for the situation in the problem. So you have the friction force is equal to the static friction coefficient times the normal. And since this is lying flat, the normal is going to be the mass of the object times gravity. And then you multiply that by the friction coefficient, static friction coefficient, and that's going to equal 10.0 to 2 significant figures. Actually, I shouldn't put the 0 in there, to 2 significant figures. The second question is what is the normal force if the normal force is 10 times the person's weight, how much is the friction on the person's legs or knees? And so you have 10 times the weight of the individual, which is its mass times gravity, and this equals 6,468 newtons. And then the friction on the knees with this level of stress is going to equal that normal times the friction force of synovial fluid in the knee. If you do the multiplication here and reduce that to 3 significant figures, you get 103 newtons. Actually, we'll put 3 significant figures here as well, because the measured value here of 66.0 is 3 significant figures. So that's problem number 3. Problem number 6 talks about a dog sled that has 8 dogs. Each dog has a mass of 19.0 kilograms. And they are pulling a sled that has a mass of 210 kilograms. And each dog can generate a force of 185 newtons. And so those are the knowns. If you draw a force a free body diagram, you have the force that the dogs generate, and it basically has to overcome the friction that's generated by the sled. And that's if you draw your circle around the entire system of dog and sled. So what this means is that the net force is going to equal the force generated by the dogs minus the friction force of the sled, and that's going to equal the total mass of both the dogs and the sled times, and that's obviously it's going to be 8 times that because there are 8 dogs, times the acceleration of the whole system. And so we look at that, the coefficient of static friction, we're starting from rest, so the coefficient of static friction is 0.14 from the table, times getting the sled moving, or the sled's normal is going to be its mass times gravity, and then that is going to equal 288.12 newtons. And so F net is going to equal 8 times 185 minus 288.12. So that's the F net. And this is, if you want to solve this equation for acceleration, you just divide that by the total mass, which will be 8 times 19 plus 210, and that's going to give you the acceleration. And so if you do the math here, this is 1480, 8 times that, and subtract that and then divide by the total mass, which is 362 kilograms, and you get 3.29 meters per second squared. So that's the first part. The second part basically says, now what's the acceleration? Now that you've got it rocking, moving, how does the acceleration change? Well, the acceleration changes because this coefficient of friction changes from static to dynamic. And the dynamic coefficient, or kinetic coefficient of friction is 0.10. And then you multiply that by the same number here, 210 times 9.8, and this time you get 205.8 newtons. And then the problem is exactly the same. You have 8 times 185 minus, now instead of this number, you have this number, 208 or 205.8, and you divide that by 362, which is the total mass, and the new acceleration is going to equal 3.52 meters per second squared. So that's the new acceleration. Now the third question has to do with the tension between the dogs and the sled. So if we draw this, now we're looking just at the sled. We have a tension force, and I want to make sure I drew the tension in the right direction. Now the dogs are pulling this way, and the friction is going, or the tension is this way, opposing the dogs. And so if we solve this for tension, the tension is in the same direction, or the tension is this way, and this is going to equal MA plus the friction force. And so this is going to equal the friction force and the opposition by the force required to cause the acceleration. So if we put this in, we have 210 times, that's the mass of the sled, times 3.29, which is the initial, which is what they were asking, plus 210 times 9.8 times 0.16 And if you add all that together, you're going to get 1020 newtons. And then that's for case 1, which is initiating. And case 2 is exactly the same, except you're going to use the acceleration for this acceleration. And so it's going to be 210 times 3.52 plus 210, 9.8. And then this is going to change to dynamic friction. And so overall, even though this number goes up a little bit, let me do a better job of writing that. This number goes down and you end up with 945 newtons. And so let me see if I can draw this a little better so you can see what I'm talking about here. So basically you have a force in this direction that's causing the acceleration, and you have the friction, and that's going to be opposed by the tension. And so the tension is going to be the sum of these two forces. And that's how we come up with this equation.